Thank you. My name is Margaret McNamee, and I'm going to be chairing the Emmons lectureship session. Okay, the Howard W. Emmons Invited Plenary Lectureship is a prestigious recognition of lifelong contributions to and career achievements in the field of fire science and engineering. Before we welcome our present awardee, I would like to take a moment to give you all a short introduction. David Purser's work covers all aspects of fire hazard development, escape behavior, and their interaction. He started working in this area during the 1970s, when the large increase in fire injuries and deaths at the time led him to study the effects of toxic smoke and heat on people and their behavior during fires. He's been a very active and influential member of our fire safety community, sharing his insights freely and generously, with his research being introduced into hazard assessment models, international standards, and incident investigations, not to mention all of his work in numerous publications and teaching. The list of specific fires that he's studied is long, including such well-known fires as the Grenfell Tower fire, the Rose Park Care Home fire, and many others. In recognition of his achievement, he was awarded, as the only person I've ever heard of in the fire safety community, a CBE, a Commander of the Most Excellent Order of the British Empire, in 2015, for services for fire safety. It's my great pleasure today, and I hope that you'll join me in welcoming my friend and colleague, Professor David Purser.
Thank you very much for your kind introduction. As the first speaker of the conference proper, I'd like to welcome everybody to Scuba and wish you an interesting and enjoyable conference. So we've already had a couple of very interesting workshops, and I see a lot of networking going on the last few days, so it's all looking very good. I'd also like to thank the IAFSS and the Emmons Committee for inviting me to present this lecture. As you can see from my title here, I want to address a number of behavioral parameters in this presentation, but also I want to talk about smoke and toxic hazards, and there's quite a bit of chemistry in there, and just a little bit of fire dynamics. So I'm hoping there's something of interest to all of you, irrespective of your particular area of interest. Now, if you know my work, you know how keen I am on ASET-RSET comparisons. And this is really because my main interest is in the survival of occupants in fires, the outcome of which really depends upon these two timelines, the fire timeline at the top and all the various stages of evacuation on the green line there. And I created this diagram many years ago for the early editions of the British International Standard of Fire Safety Engineering. And I think it's very useful because it highlights the main stages and gives us a chance to identify these stages and then go out and quantify them, as we've been hearing with Rita's work. And also, I think it's very good because it concentrates the mind of anybody doing a scenario analysis. If they spend all their time, for example, calculating travel time, they really need to look at this and assess, have we really addressed all these other issues that are so important in the processes? And I noticed a big change over the years. So when I first started coming to IAFSS meetings, I think the first one was in the States, in Washington or somewhere, our views in those days on human behavior tended to be rather simplistic, and still are in many of the codes, so that we would assume that once a fire started, it would be rapidly detected by some system or a person, and then there would be a warning issued, and everybody would immediately go into the travel phase of the evacuation and all get out of the building during this period with a wide margin of safety. But we know that in practice, things are a lot more complicated, and there's a lot of time can be lost and varying things can go on during the detection and warning processes. Then there's all the behaviors that people go in before they actually start to travel. But I've been finding this approach to things, the ASET-RSET comparison, very useful in my work investigating quite a few important fire incidents over the years. And basically, evaluation of an incident scenario involves data and calculations for many parameters and interactions. You really have to look at the whole picture to understand what happened in a fire incident. So assessment of the development, occupant behaviors, and effects of toxic smoke exposure during actual incidents can provide a reality check on our engineering methods and data quality. Because the outcomes of any incident are known, they constrain the prediction from the fire scenario, evacuation, and toxicity modeling calculations. This enables validation of current methods and may reveal previously unidentified or inadequately characterized features. I'm just going to quickly pass on to, so I've decided to try and address the following topics in this presentation. I want to talk about pre-warning delays, a neglected parameter, but with a very high consequence for survival outcomes. I'm also going to talk a bit about the effects of cues and warnings on occupant behavior and pre-travel times in incidents, the probability of entering and evacuating through irritant smoke, people's decision whether or not to enter a smoke-filled escape route, very important. Stair descent speeds of mixed populations through light and dense smoke, and then exposure times to incapacitation from asphyxiant gases for effluents from different fuel mixtures as a function of smoke density, using smoke and CO exposure, toxicity, and blood carboxyhemoglobin forensic data to estimate the development and exposure history. Right, on pre-warning time, I'm going to very briefly go through this. The time to detection and warning depends on the dynamics of the detection systems and the management protocols. In a complex system such as an occupied train or an underground station or a tunnel, detection may occur several times by different mechanisms which may or may not then lead to a warning to affected occupants. For example, a passenger might see smoke and telephone the emergency or management, but the emergency may not be recognized at that time as important. They'll just send someone to have a look. And so time may be lost. And the outcome of all this, at the bottom of the page here, is in this situation you get a sort of subroutine of different detection and pre-warning events, which occurs before a general warning is given to the affected occupants. So in my little diagram at the bottom here, if that's our escape equation, somebody detects a fire, reports it to somebody else, who then somebody sends someone to have a look, who then reports back to their boss, and you get this kind of loop occurring for some time before somebody says, hey, this is getting bad, we really need to get people out now. And only then does a warning get issued. And I did some work on this some years ago involving Steve Gwynn, Sekizawa, who I saw in the audience earlier. And so we have a number of publications on that. But I think it's still a parameter that is not taken seriously enough. Just to very quickly give you an example, I've published this before, but also the Dusseldorf airport fire, you may remember. This happened with hot work on a road which formed the ceiling above the arrivals area. And the fire was spotted by a taxi driver who was dropping a fare off at the departures level above. It's about here. So the taxi driver reported a smell of smoke and sparks on the taxi roadway. So that's time zero. That was the detection of the incident. And 2 airport firefighters were sent to investigate. And then you can see this long, long timeline of various activities carrying on, none of which involved warning the general occupants, until finally, 35 minutes after the initial detection of the fire, an automatic alarm, voice alarm system instructed people to evacuate, actually sent them in the wrong direction towards the flashed over area of the building. So there's definitely issues here about recognizing the importance of early signs of fires and making an appropriate response that we really need to concentrate on. Issues concerning the long investigation period, the chains of reporting, and reluctance to issue general alarm warnings. Now, I want to leave that there, but I want to pick up on the same tack to do with residential fires. Now, just to briefly summarize, the UK building regulations for any occupied space require the mission statement, if you like, of the UK building regulations, is that you have to have some means of early warning of fire a means of escape to a place of safety outside, capable of being safely and effectively used at all material times. So that's our general mission statement. But for multi-story residential apartment buildings, that is satisfied by having smoke and heat alarms in each individual flat, and fire-resistant construction between the flats, and protected escape routes via a protected lobby to a protected stair. So occupants of an affected flat can be alerted and escape via a smoke-free escape route with fire contained within the flat of fire origin. That's the theory. Simultaneous evacuation of the building is regarded in the regulations and the codes as being unlikely to be necessary. So occupants of other flats should be able to shelter in place, but they should always have the safe escape route if they need to evacuate. And that's really quite good, works reasonably well most of the time. But unlike public buildings, there's generally no communal warning system, so there's no means of alerting the whole occupancy. And there's no 24-hour on-site fire safety management that you would expect to see in something like an airport. And really, there's no plan B. If the building fire performance goes wrong, you don't have a backup, other than individual occupants making their decision to leave, or at some point, management due to the fire service incident management. And this is starting to show up as a problem. Particularly, it drew my mind to it was the first incident in London in a high-rise block, or medium-rise block, which involved a cladding fire, spreading cladding fire, which started on a sunny afternoon in the summer. I think people in the building, a lot of them were watching Wimbledon tennis, and the fire service were called quite quickly. But the occupants, the fire occurred on the 9th floor, occupants on the 11th floor were advised to stay put when they called the fire service, and were in contact with them over some period of time, until eventually they were overcome and died in the fire. So there was a pre-warning, if you like, delay of at least 22 minutes when some action could have been taken potentially for those people, as attention was drawn to this by the coroner's report after the event. So then imagine my surprise when a few years later in the same city we had the Grenfell incident, much more serious, starting just before midnight on the 14th of June 2017, resulting in 71 official deaths at or just after the fire scene. One person died some months later, making it 72 arguably. Now this started at 0054 hours. The fire service were called and there was a fire in the 4th floor flat 16. But at 0115 hours, the fire broke out into the cladding and installation, and there was a very rapid fire spread over a period of about 13 minutes, as you can see in this picture here, all the way up to the crown of the building. And at about 1:25 to 01:30 hours, the lobbies on all the floors became completely smoke-logged. And so people became trapped in the building. And by about 1:40, that smoke had got into the stair. But it wasn't until 02:35 that the fire service advice changed from stay put to evacuate. So the pre-warning delay between the fire being reported and instruction to evacuate was 1 hour 41 minutes. Now you could say, okay, well, you wouldn't expect to call a main evacuation just for a fire in one flat, so that would be appropriate. They wouldn't do it when they fought the fire in the first flat. But once the fire had broken up and gone up the cladding, we still had 1 hour 20 minutes from the start of serious fire spread before the evacuation warning was given. So a big pre-warning delay. And there was actually a 35 to 40 minute time window for safe evacuation from the start of serious exterior spread. So the occupants were in communication by landline with the authorities and with each other. And a lot of people were using mobile phones to talk to their neighbors and relatives outside the tower. And there was an intercom call system in the lobby which could be linked to each flat. And that was used on a few individual cases. Okay, so I'll leave that there and say pre-travel time, pre-warning times is a big, big issue that we really need to consider seriously in IAFSS going forward. Moving on to the next parameter, pre-travel times at Grenfell. Now, we've just been hearing already about the expanding published database of pre-travel time distributions from different occupancies other than residential. Nearly all our funding for this work is for public buildings, large buildings. And I started working on this in the early 90s to try and get some quantification, working a lot with University of Ulster. And there was a number of, but I was going to draw attention to something that's already been mentioned, the publication by Lavriglio, Gwynn, Kuligowski, and Boyce on, we're now getting, over the years, we've got a really good database of pre-travel time distributions built up over the years. But we really lack a good similar database for residential buildings. And Grenfell actually does provide us with an opportunity to get some data for one subset of the occupants. And that's the occupants of flat 6 on each floor directly above the fire. So we know exactly when the fire appeared outside the kitchen windows of each of those flats up the tower from the videos of the external fire. And we also know what the occupants did, because I've spent many years now studying their witness statements and looking at their timelines of their activities. And what we find is that the means by which people were alerted, which is in this table here, were mostly by the smoke and heat detectors in their flats going off. So you could say that the system was working in that sense for individual flats. A couple of people realized that there was a fire by smelling smoke before their alarm went off, but it then went off. So that was fairly successful. But what I've done here on this diagram here is I've compared the time people evacuated their flats into the common lobby relative to the time of the fire appearing outside their kitchen window. And I'm pleased to see that in the majority of cases, people were out of those flats within 3 to 4 minutes of the arrival of the fire outside. And when reading their statements, they were very, very highly motivated to get out. They woke up very quickly when the fire alarms went off. They saw this big fire outside their kitchen. They rushed back to warn other relatives, grab essential items, which were mostly passports and mobile phones, and sometimes ran out without even putting their shoes on. So a very good, sharp response. And I think that's quite an encouraging little data set to show that domestic smoke detectors really can work in certain situations. Moving on to the stair descent, I want to talk a little about the performance of the stair. There are many published experiments of descent rates and flows on stairs. How well do these agree with the mixed age and ability population, including children and elderly, and with various abilities and disabilities, as we had at Grenfell, a really mixed population? Well, occupants descended individually at Grenfell or in small groups over an extended period, so there was no congestion in the stair. It was essentially an unrestricted descent. The flat exit times were estimated from witness evidence and phone calls, tower exit times, and measured with a CCTV at the bottom of the tower. Figure 3 shows the calculated exit times for the flat 6 group. And I want to just draw your attention here to the red squares here, which are my estimates, the open squares here, which are my estimates of the predicted time to evacuation from the bottom of the tower, assuming that people took 12 seconds to descend each floor. And you can compare that with the red triangles, which are the recorded actual times that they exited the tower. And you can see a fairly close correlation. We've got a little bit of actual data here. There's one D. Purser, who, when I went to investigate the incident, wearing heavy boots and protective clothes at the age of 73, I tried to hurry down the Grenfell stair, and I managed about 9.3 seconds per floor, which I don't think I could do now, but anyway. And that correlates quite well with a published paper by Choi and Gallia's group of 9.6 seconds per floor for males, 10.2 for females. And there's just a couple of people here who, from the actual incident, who descended in the smoke-free stage of the incident, and they took between 8 to 12 seconds per floor, because they made a phone call just before they left the flat and entered the stair, so we have pretty good timing data for that. Now, looking at the stair capacity of Grenfell, it was a narrow, single 1 meter wide stair. Did this limit the evacuation? Some people said it would have been a big problem to have evacuated that tower quickly because of the narrow stair, single narrow stair. Well, just looking at Jake Paul's sort of basic approach to this, a 1 meter stair gives you a maximum flow rate on the stair of 42 persons per minute, right? And there were 293 people in the tower, so the sort of default time is it would have taken 7 minutes to, if everybody had leapt into the stair immediately, they could have got out within roughly 7 minutes. Obviously, 1 or 2 people would be a little bit slower or a bit faster. What about the density on the stair, if that had happened? Well, because it's, if there was a simultaneous event, there would have been about 13 persons per floor on the landings and steps between floors, which gives you a density of 1 person per meter squared. So you can see that it's really a very low density event. And of course, in practice, it would have been much less than that because we know that we had a pre-movement time distributions of people who are coming out at intervals. And the actual unrestricted descent time is between 0.2 and 5 minutes, depending on which floor you start from. So this confirms that for residential buildings, the low occupant densities ensure that even minimum exit and stair widths allow sufficient standing and flow capacity for even total immediate simultaneous evacuation without the risk of congestion on the stairs. This figure here shows the actual pattern of evacuations in terms of the time people entered the stair from different floor levels. And the blue here is floors 4 and 5, the fire floor and the floor above. And then I've done it in sets of 6 floors. So that's the lower 6 floors, the middle 6 floors, and the upper 6 floors. And the red line here is the time that the lobbies became heavily smoke-logged. And you can see that a lot of people had evacuated quite quickly of their own volition before that time occurs. There's a problem on the upper 6 floors. Only a few people came out. And the reason for that is a cluster that formed. So 18 persons from the upper 6 floors entered the stair and started to come down. And somebody below shouted, "Go back, you must go back." And so they all turned and went back up the tower and took refuge on the upper floors. As they did that, they inhibited others who were planning to just come down from entering the stair. And the result was there was a lot of deaths in those upper 6 floors. Although at the time, the stairs were pretty clear of smoke, other people were having no problem getting out. In fact, one person in that group went down, went back up to her flat on her upper floor, and then said, "No, this is wrong, I want to get out," and left this group and successfully got out. Oh yes, and then after that, everybody remaining was trapped by the smoke. But then as the fire moved around the tower and attacked the flats from outside, it caused people to have a second wave, if you like, of evacuation over an extended period from 2:18 to 08:07 the next morning. And that's shown in these lines here. Okay, now moving on to the next parameter of irritant smoke. Now, irritant smoke affects the probability of occupants entering and continuing to evacuate or turning back in an incident. I think that's the most important parameter. It also affects walking speed and wayfinding as a function of density and irritancy. And there's also the time of exposure to asphyxiant gases in smoke and distance walked before collapse would occur. So if you're walking through smoke, that smoke contains carbon monoxide and cyanide, which after a period of time will cause you to collapse. Now, I want to just focus a bit on some work by John Bryan, we heard about earlier, and Peter Wood in the UK, who did some very useful work on this, but quite a long time ago, on incidence data of people's response to being exposed to certain concentrations of smoke. And basically what they found was that when the visibility for reflected signage or walls got down below 4 meters, then increasingly a very large proportion of the population is going to turn back or fail to enter rather than continue through smoke. So it becomes a very important aspect of trapping people in a fire scenario. From my own experience of this, I experienced it a lot with the investigation of the Mont Blanc tunnel fire. If you can remember, a lot of vehicles were trapped on the French side of the fire, and all those vehicles were enveloped in a thick cloud of smoke coming down the tunnel. And the key point about this was that although a few people did get out of their vehicles and try to walk down the tunnel, most people stayed in their vehicles and then died there. They were very unwilling to get out of their vehicles into the smoke. But at Grenfell, this was very important because many flat occupants were unable to enter and cross the dense, irritant, toxic smoke, despite making repeated attempts. So they'd open their flat door, they'd see this thick smoke in the lobby, and they would just have to go back and take refuge in their flats. Others, though, a small proportion, succeeded with difficulty to cross the lobby and enter the stair. But once they got in the stair, which was also smoke-logged, 58 persons of mixed ages continued down to the ground floor, holding the handrail as guidance. And what struck me was that once people were committed and in the stair, very few people then turned back once they'd committed themselves to that. So again, I would say that looking at the behavior in relation to facing dense irritant smoke is something that we really need to take much more seriously and do a lot more work on. So I'm giving you fuel for your future research applications here. You can quote me on this. Okay, walking speeds in smoke. Well, we've got a lot of very good experimental data on walking speeds in smoke, a lot of it done at Lund and places like that. And how well does that map? And of course, the Japanese work of Professor Jin. How does that map on an actual incident? Well, we've got some quite nice data for a few people in Grenfell, and here's the same table I put up earlier. So here is the top part is the movement in clear conditions. What happens when people are in dense smoke is that their travel speed drops to about a third what it was in the relatively clear conditions, which is a very good agreement with Professor Jin's work, where he showed that in sort of dense smoke conditions, people walk at about a third of a meter per second compared to just over 1 meter per second under normal conditions. So I think that's interesting because the bit of data there, the Grenfell results, seem to fit in quite well with the experimental data that's been obtained. That's quite encouraging. Now, the rest of my talk, I want to try and focus on toxicity. I think I'm going to have to hurry up a bit here. Incapacitation or loss of consciousness followed by death from asphyxiant gases results mainly from exposure to CO, but also cyanide, and with some contribution from carbon dioxide and oxygen. And it depends on the time concentration curves of these gases in a full-scale scenario. But the term in the handbook, if you look at it, for the dose of CO, actually calculates the carboxyhemoglobin buildup in the blood of the exposed person and expresses that as a fraction of the dose required, the carboxyhemoglobin level required to cause unconsciousness, which is 40% approximately COHB in a resting person, or 30% in somebody walking, for example, down a stair, whereas 50% is lethal. Cyanide's a bit more complicated. It's more concentration related. Now, basically, if you want to do an analysis of conditions in an incident, there's 3 possible methods you can use to do this. And one of them is to do a full-scale incident reconstruction with direct measurement of the toxic gases and the heat and smoke in your reproduction test. So that avoids the need to do the fire dynamics modeling. Alternatively, you can try CFD or some other method of fire dynamics modeling coupled with yield data to get the time concentration curves of the fire. And a third method, which I've been working with, is where modeling is difficult for complex scenarios. We can estimate the smoke obscuration and visibility from witness evidence, and then the CO2 and cyanide concentrations from measured smoke and gas yields test data. So essentially, the smoke and the gases track together. So as the smoke is diluted, as the plume flows away from the source fire, so the CO and the cyanide in it equally decreased, but the ratio stays roughly constant. So just very briefly, this is an example where we did a reconstruction test. So this was the Rose Park care home fire. There was a bad fire in a cupboard here, opening onto this corridor, which led to the bedrooms of the occupants. And there's our reconstruction fire test. And I then did FED analysis to forward predict what would happen to the occupants exposed to these conditions. And part of that, I calculated their uptake of carbon monoxide. So I calculated their COHB concentrations at the time of rescue if they'd have been exposed to exactly the same conditions as in our reconstruction test. But of course, in all these cases, how good is the reconstruction test in representing what actually happened in the real incident? Well, we have a handle on that because we have the hospital carboxyhemoglobin data for the victims. And we can compare the two. We compare the forward prediction with the actual amount in the blood. And what this showed was there was a pretty good agreement for all these rooms off the actual fire corridor. So we felt confident that that was supportive of that our test was a good one. But for the people, as the fire burned, there were aerosol cans in the cupboard which kept exploding, and the pressure pulses blew open the fire door between corridor 4 and corridor 3. So there was a lot of smoke in corridor 3 and the rooms off it. And when we forward analysed that, the level of carboxyhemoglobin predicted from the test data was somewhat lower, considerably lower, than the actual hospital data. So there was a discrepancy there. When we went back and looked at the situation, we realised that there was a smoke and air extraction system over the cupboard and the corridor here, which was dumping smoke down into corridor 3, which we showed up in large-scale tests later on. When we allowed for that difference, we found there was a good match with the toxicity data. So I hope you can see how using this combination of approaches, a test, FED analysis with forensic data, you can build up and validate your scenario. Another one here is the Mont-Blanc fire, where we use CFD analysis. My colleagues, Professor Cox, Kumar, Stuart Miles, did the CFD analysis. How am I doing for time? I've got to hurry up. So basically, they did a forward prediction of the fire conditions, and I applied yield data and FED modeling to calculate if people were exposed to the CFD modeled fire, how far would they be able to walk down the Mont Blanc tunnel towards France before they would collapse, and at what time would that happen? Then we were able to compare that with the actual position in which the bodies were found and the calculated time they arrived there from the arrival time of the vehicles, and we got a good match. So again, a combination of the CFD modeling with the FED modeling and the forensic data gave us comfort that we had a good representation of the conditions that actually occurred. And of course, there were other CFD measurement models which were with slightly different parameters. And the main scenario 0, was the one that best fitted the actual data. Now, for all this, you need toxic yield data. Where do we get that from? Well, that's why we created the tube furnace method, where we could measure the yields of toxic products from a whole range of materials under well-defined conditions of temperature and equivalence ratio, flaming and non-flaming behavior. So this gives us a good database. And this was done, a lot of work was done at BRE by myself, particularly by my wife, Dr. Jenny Purser, and also, and subsequently and continuingly at UCLan with Professor Steck and Hull, and also in SP in Sweden and in Canada. So we have a good validated database now, which I encourage you to start using in your calculations. But what I wanted to talk about now is this third approach to the problem, where you can't really do a test, and you can't really do a straightforward CFD analysis. I've been developing this idea that we can get some quite good predictions of tenability by relating them to smoke density. And I presented this originally for tunnel fires. So we took a mixed fire load, and if you measure the yield of smoke particulates, CO and cyanide, hydrogen chloride, you can use those ratios between those concentrations to predict what's going to happen. So for example, to give you a simple limit, if you can see 10 meters in any fire, then by definition, if you like, the concentration of asphyxiant gases in that smoke is going to be so low that you could walk through that smoke for at least a couple of hours before you would become incapacitated. I mean, you might have health effects, but you wouldn't become unconscious as you try to walk out. But once you get up to about 2 meters visibility, then that correlates with a few hundred parts per million of CO and cyanide. And you can see then as the smoke density increases or visibility decreases, then the concentrations you're exposed to go up very quickly. And I can do FED calculations to predict how long people could walk through that smoke if it maintained at that concentration before they would collapse. So you can see that with 4 meters visibility, you've got at least 90 minutes or so to get out for the average person and half an hour or so for the 1% of the most sensitive people in the population. Even for a 1 meter visibility, you've got about 18 minutes time you could walk through that before you would collapse. So for Grenfell, we want to establish the exposure conditions throughout. And it's very challenging to do any kind of modeling of that, the conditions inside the building in each individual flat. With a fire and smoke-filled flat 6 on each floor, and from there the lobbies were filled with very dense smoke by 1:30 hours. And smoke from the lobbies then gradually penetrated the flats around the tower on each floor over a period of several hours. So there's a group of people who are trapped in separate flats, and the smoke is coming in from the lobby around their doors, leaking around their doors and filling their flats. How bad was that smoke? The fire then spread around all 4 sides of the tower, and as it went past each flat, it broke in, and so you were then getting more toxic gases coming from outside. But as the fire went, the cladding fire moved sideways around the tower, it only burned for a few minutes before the fuel was used up. And you can see that in this picture here. So the initial bright fire was in the middle here, directly above the flat of origin, but that's then gone out as the fire is moving north and south in the 2 directions. And from this succession of pictures, you can see it's sort of probabilistic when any individual flat would start to catch internal fires. Sometimes it was half an hour, sometimes an hour or so. So eventually, all these flats are completely burned out. So there's no sort of time information available unless we use the witness statements and things. So what I was trying to establish with this work was the extent of smoke penetration from the lobbies into the flats and the CO exposure of the occupants sheltering in the flats before the arrival of the exterior fire. How bad was that long period when they were trapped there with smoke leaking in? Once the fire got outside the first room of any individual flat, how much was the extent of penetration through the flat to the shelter rooms? So if we look at, for example, here, the flat 5 situation, the fire's moving across the north face of the tower and first of all breaks into one of the bedrooms in flat 5. The occupants are sheltering in the living room lounge area at the corner here. So they've got some protection even after the fire starts to attack the first bedroom. And we have some data on that from their witness accounts. Once the fire then came outside the room where they were sheltering, that's when conditions deteriorated very, very badly, very quickly. Then we have the situation where some occupants evacuated before or immediately after the exterior fire arrived. So they've got some cumulative uptake in the flat, and then as they cross the dense smoke in the lobby to get to the stair, and then in the stair itself as they descend, before they reached the bottom of the tower and walked out. So how bad was the conditions there? And why was it that 58 people were able to descend the stair after 18 hours up to 8:07 hours and survived, while 15 people collapsed and died in the lobbies or stair, 2 pronounced dead on arrival at hospital, and 53 died in their flats? What was going on there? So my first estimate was based on the witness reports of the smoke density, and from that implied carbon monoxide concentrations. And I used a sort of iterative approach. For yields, I did a new set of calculations to measure the yields of and the exact fuel load in a typical flat. So the mass of fuel in the flat, but the mass of each type of fuel and the mass of carbon and nitrogen and chlorine in each of those materials. And what I found with that was that if you look at the whole fire load of a flat, imagining complete burnout, then it's dominated by cellulosic materials. If you think of your own flat at home or house at home, the totality of the fuel in there is very much cellulosic with bits of added furniture. So what I found was that the percentage of carbon in a typical flat was 47%, which is pretty typical of any fire load. But what I was particularly interested in was the percentage of nitrogen, because that's where the cyanide comes from, nitrogen in the fuels. And it came out at 3.7%. Now, normally I would say, if you've got 1% nitrogen in your burning fuel load, you can forget about cyanide, it's not going to be a problem. But if you've got more than 1%, cyanide is something you need to consider. And so this is in this middling range where the toxicity I knew was going to be dominated by CO, but there would be a contribution from cyanide. And then I took tube furnace and other yield data according to the masses present to work out the ratios of the gases in the plume. The basic outcome of this was that the flat occupants who were trapped in their flats were alert and able to shelter in closed rooms for up to several hours from smoke penetrating from the lobbies. The visibility, they reported, was several meters. They could sometimes open windows on the side away from the fire. And so they were obviously exposed to quite low concentrations of carbon monoxide. But after the exterior fire came around to the first bedroom, then it would increase a bit more. But then once it got to their shelter room, outside the shelter room, there was sudden massive filling with very dense toxic smoke. The flat contents and the bodies were then eventually burned. But the tissue remains that we did get showed very high carboxyhemoglobins in the remains, indicating that they died from smoke exposure and that the fire consumed the bodies maybe some hours actually later, up to. And in fact, 3 occupants fell from the tower, fell out of the windows of the tower, just as the fire was coming around to their shelter area. 2 of them had 20% carboxyhemoglobin, confirming that they had a relatively minor exposure up to that point, but then increasing. 1 had the young man succeeded in getting out of the window and falling from an upper floor, even though he had as much as 50% carboxyhemoglobin in his blood, which is pretty well the threshold for lethality. So the data we did get for those who died in the flats or died in the lobby or stair immediately after leaving the flat was that they all had very high lethal concentrations of carbon monoxide. I just want to briefly now talk about how I used this iterative method to try and understand particularly what was going on in the stair. So if you think of somebody coming down the stair, what's important is the average concentration of CO that they're exposed to over the whole time they're in the stair column. Doesn't matter if it varies a bit, it's the average, it's the area under the CO curve that's important. And I can apply a COFD analysis to that, FED analysis to that. So I, based upon the smoke density, I estimated that the concentration, average concentration of smoke in the stair at Grenfell was around about 2,000 ppm. Knowing that, I could then calculate what carboxyhemoglobin people would reach by the time they walked down to the bottom of the stair. This shows data for 2 actual people who descended from the 22nd floor. And importantly, when they got to the bottom of the stair, they reported one of them collapsed, and had to be carried out, and the other one felt dizzy but managed to walk out on her own. So I could tell they were just at that threshold of collapse, meaning they had about 30% carboxyhemoglobin in their blood, which was later confirmed by their hospital blood analysis. So I could then model this uptake, and in the blue curve here, I've assumed they were exposed throughout to 2,100 ppm of CO. And doing that does indeed give me 30% by the time they reach the bottom of the stair. So that's kind of in the money. But if I increase that by about 20-odd% to 2,600 ppm, it doesn't work because they would have collapsed much higher up in the tower. And if they were only getting 1,600 ppm, then they would have only got to 20% carboxyhemoglobin and would have been able to walk out unscathed. So you can see it homes in on quite a narrow range. Now in practice, of course, they had some exposure in the flat before they left, and we need to take that into account. They had to cross the lobby, and then they got the stair. So this is my analysis of that. It looks a bit complicated. So here I'm making an estimate of from the witness statement of the sort of CO curve, the black here, they were exposed to in the flat. Then they get exposed very briefly to a high concentration while crossing the lobby over a few seconds, and then 1,800 ppm for the rest of the way down. By looking at a load of people, I came up to the conclusion that the actual concentration in the stair was about 1,800, right? So if I apply my analysis to that, this is their COHB uptake curve, and we start from the end. So it's got to end at around about 30%, 34% carboxyhemoglobin, which means I then know, that because there was 1,800 ppm inhaled, that when they enter the top of the stair, they already had 9% COHB in their blood, which is really quite a low level, non-incapacitating. So this confirmed that the exposure to smoke while in the flats, before the fire got round to them, was relatively low. Now, of course, we have to take into account the other gases, and I'm going to have to prove on there. The blue curve there shows this minor concentration of cyanide. Right, I'm just going to quickly, no, I think I'm nearly there, actually. So all this was based upon the concept of the carboxyhemoglobin in their blood relating to the symptoms that they reported. So I'm saying because they were on the verge of collapse, it must have been about 30%. But I can do better than that because for 21 survivors, I have all their hospital data. And here, when you leave a building having inhaled carbon monoxide, as soon as you get out to air or you're given oxygen by the ambulance crew, you start to wash out the carbon monoxide with a decay curve, an exponential curve, which published data gives a half-life of 74 minutes if you're breathing oxygen. So I fitted a best fit curve to the data for those pooled data for those 21 people who left high level flats. And you can see that back extrapolating that the time they left the tower indeed comes out at about 30% carboxyhemoglobin. So they really did have around about 30% when they left. A few people who were left lower down the tower from the 12th floor, only going halfway down the tower. So they, as you can see, they had a much lower level and were unscathed. Now, it's possible that the CO concentration changed slightly with time. And so I plotted that, which shows there's no trend with time. There's more detail in the paper explaining this. But if you compare it with the floor they started from, you can see there's a positive correlation, as we'd expect. Finally, apart from the asphyxiant gases that you're inhaling, you have the problem that you're inhaling smoke and irritant chemicals associated with the smoke. And this can cause lung inhalation injury, which develops in the lung usually quite a few hours or even a day or two after you leave the fire. And interestingly for Grenfell, a lot of people who were rescued alive or walked out alive but with bad smoke exposure had quite serious lung complications. And many of them were put into induced comas and ventilated for several days and treated until they were able to breathe for themselves. So what I did with from their anonymized hospital data was I scored their extent of lung injury on this table here. And I plotted the extent of lung injury against the carboxyhemoglobin concentration when they left the tower. So obviously the more CO you inhale, the more particulates you're also inhaling because the two are together in the smoke. And what we found with this was that there was indeed some sort of positive correlation, a bit of a scatter here. And it was a sort of threshold around about 20% carboxyhemoglobin. So what I'm saying is, if you inhaled smoke sufficient to give you 20% carboxyhemoglobin in your blood, then the irritant particulates coming with that are sufficient to put you on the threshold of quite significant lung injury. And that equivalated to inhaling about 200 milligrams total of smoke particulates, with 300 milligrams causing severe symptoms. Okay, so I'm going to finish my presentation there. I won't go through the conclusions. You can see them for yourselves. I hope some of these parameters, it's all a work in progress. Please go out there and get more data. And I hope I've inspired some of you to pick up on some of these parameters and go and get better data for them. As I say, I hope it's useful for you in your future grant applications. And I'll leave you with that. Thank you for your attention.